All right, guys, today we are wrapping up chapter 3, and what we're going to do today is we are going to look at chemical formulas. We're going to look at what do they tell us, how do we make them, and after we know what chemical formulas are telling us, and after we know how to make them a nice, good, rounded, balanced chemical formula, how do we name them? So 3 main things today: information in a chemical formula, how to write a balanced chemical formula, and then how to name our chemical formulas, because what good is making them if you can't, like, name them or even say what the heck they are? So let's get to it, guys. And the first thing that we're going to look at today is, well, what is a chemical formula? And there's actually more than one kind of chemical formula. There's actually several. But what we are going to look at is this guy right here. It basically describes the composition of elements and compounds. It tells us what's in a compound. I mean, that's like the main job of a chemical formula. It tells us what's in there. Now, there's actually several kinds. The first kind that we're going to look at is this thing, is the molecular formula. Now, I want you to, I'll leave it like that. So what it does is it tells us the total number of each element in a molecule. Tells us how much of everything, and this is a lot of stuff that you guys already know. We've been talking about some of this in lab. We've been talking about it like all year, but now we're going to put names to it, and we're really going to dig in specifically to what information is there and how to find it, right? So the corners around an element have meaning, right? This corner here is for mass. This corner here is for atomic number. This corner here is for charge, but that tells us how many atoms, right? So if you see F with the subscript of 2, that tells us that there are 2 fluoride atoms in that particular compound. Just like in H2O, there are 2 H's, right? That's that little teeny number at the bottom right tells us how many. And also, just one little thing, like okay, this oxygen, this little subscript E2. The subscript means or tells 2 of whatever is right next to it. So this 2 says that there are 2 hydrogens. And if you look at this oxygen, y'all see ain't nothing there. But there's at least 1 oxygen. So if we put oxygen, there's at least 1. And we'd like to keep things as, as lazy as possible. So if we don't have to write the number 1, we don't. So we really don't. So what this is telling us, H2 means that there are 2 hydrogens. Right? And the fact that it's just O with no real number added, right? So this tells us that there's just 1 oxygen in H2O, right? So this is stuff that you guys already kind of knew, but now we're going to get a little bit more specific, and the way we're going to get specific is with this thing right here. We're going to start using the word subscripts a lot. Like the word subscript shows up in this class like constantly, and the subscript. It's what we need to really have dialed in about subscripts is that these are the subscripts. Actually, the fact that there's no subscript there counts. These are subscripts. These are small numbers in the bottom right-hand corner that tell us the number of atoms in the molecule. Okay, it is always on the bottom right, and that's the 4 corners. Remember the upper left, mass, atomic number, charge, and now this. That is your subscript. That tells you how many atoms of that element are in that particular compound or polyatomic ion or whatever the heck it is that you're looking at, because you're going to be looking at a lot of weird stuff. Now, a coefficient, this is the word coefficient. This is another kind of like big number, but this one is going to tell us not how many elements there are, but how many whole molecules you have to like all together, right? So like if we're talking about puppies and I say I have 2 puppies, I say 2 puppies. And this is your coefficient, right? It's the number out front that tells us how many things we have, okay? And so that coefficient and that subscript, they're going to start working together for us to be able to count the number of actual atoms in a sample or in a chemical reaction or like whatever. And this is sort of setting us up. This is a skill that we need to have to move on to like chapter 4 and 5 and 6 and 7 so we can start counting atoms and see how the atoms start to interact with each other. Does that make sense? So this coefficient or like the big number out front, this tells us, that number tells us that there are 2 water molecules. Does that make sense? And so you're going to be asked, how many water molecules are there? Like, how many molecules are there? Well, there's 2. You're also going to be asked, how many hydrogens are there? How many oxygens are there? And it works like this. There are, let's do the hydrogen first. There are 2 water molecules. Okay, each water molecule has 2 hydrogens. How many hydrogens in all? Well, if each one has 2, and there are 2 of them, I think the math word that we talked about is that the distributive property? I don't know. Don't tell the math teachers I don't know the names of all the math stuff anyway. But that's what it is, right? It's 2 times 2, so you're going to get 4 hydrogens. Yeah? I hope that's right, because, whoo, boy, if I do that math wrong. Okay, so the next one is for oxygen. Well, it's sort of the same thing. There are 2 water molecules. Each water molecule has 1 oxygen. How many oxygens in all? There are 2 O's, or 2 oxygens. You guys see how that works? Yeah? This is a little thing like this, atom counting. Super important moving forward. So we're looking at it now. When you look at this here chemical formula, let me clear this all up here for you. When you look at this chemical formula, what I need us to start really like honing in on is I need us to start looking at this number and that number and seeing how they relate to each other, right? Because this number tells us, the coefficient tells us how many molecules we have, how many big whole things, and then this little subscript tells us how many of the little pieces are in each one thing. Got it? I hope so. I know you do. Moving right along, now that we know all about the molecular formula, we're going to move into this thing called empirical formula. Now, empirical formula is used for something like this, right? You see this little plastic container, right? Okay, this is all one molecule. This is one giant molecule. There are more atoms in this plastic container than there are people on Earth. They're guaranteed. There are so many atoms there. And we're never going to be able to count that many atoms. So the chemical formula for that particular molecule is not going to work out. However, it's a polymer, which means it's just the same thing over and over and over. And it's the ratio of carbon and hydrogen and oxygen, and I think there might be sulfur or something in there, maybe nitrogen, but mostly carbon, hydrogen, and oxygen, just repeating over and over and over. And it's that ratio of those elements that determine what kind of plastic it is. So like when you go to the recycling center and you'll have number 1 plastic, number 2, 3, 5, number 5 plastic. It's all just a different ratio of elements that make up those different plastics. So instead of trying to write the actual chemical formula for this entire huge molecule, we break it down to the simplest ratio. And there are other purposes for having this empirical formula that we will visit next chapter, but not so much right now. We're just going to be introducing ourselves to it. But there is a purpose for it. We're not learning this just solely for the heck of it. So this is the simplest ratio of atoms in a chemical compound. So we break it down to just the ratio. And for ionic substances, it's already there, right? So here's NaCl, sodium chloride. And what this tells us is that for every 1 sodium, there is 1 chlorine. It is already as simple as possible. Does that make sense? So in this case, the molecular formula is the empirical formula, or the chemical formula, because it's not a molecule. You know what I'm saying. And by the way, we're going to be using these words totally interchangeable. Molecular formula, chemical formula. I'm not going to hold you too much to it. So let's keep going to glucose. Now, the molecular formula for glucose is C6H12O6. Now, the empirical formula, or the simplest ratio, what we have to do is try to simplify them down as much as you humanly possibly can. And people who know the math term for this, I'm sure, are going to do better. But it's just simplifying, right? divide it by the least common denominator, the greatest common factor. I don't know what it's called. You simplify. So it breaks down to 1 carbon, 2 hydrogens, and 1 oxygen, and that is your empirical formula. Yeah? Right now, it's just a matter of learning what the empirical formula is and practicing figuring it out. Those are the 2 things that you guys got to do. We will take it to the next level, like how and why we use the empirical formula and in what scenario we use it. We'll look at that next chapter. Let's at least learn what it means for right now. You know what I'm saying? So let's just dig into these. Here we have 2 molecules, and we're going to find the empirical formula. So here's C3H12. Now, if we're going to simplify these down as simple as you can get, C3H12. It's even. I can't divide by 2. So I think it's 3. So if I divide both sides by 3, I'll get CH4. There. That's, yeah. Multiplied by 3. That's, yeah. Okay. Yeah. So that's my empirical formula. Now this one, 20, 10, and 5. I can't divide by 2 because that's 5. I think I'm gonna divide everything by 5. I think that's gonna work out for me. So that's gonna be C4H2O. Is that it? Yeah, I think that's it. Let me see. Multiply everything back by 5. So what I'm gonna do is I'm gonna check. So I divided everything by 5. I'm gonna multiply by 5 again. So that's 5. Yeah. I think, and I can't get it any simpler than these because there's only 1 of carbon and 1 of oxygen. So yeah, that's as simple as I can get. I'm gonna call that good. I hope you guys agree. If I did it wrong, let me know. Wouldn't be the first time. Sorry, I want to review. We have molecular formula. We have empirical formula. Molecular formula tells you all of everything that's in the molecule, the total number of each element, right? That's what your molecular formula tells you up here, or your right. How much of each and every one. The empirical formula gives us just the ratio, like the simplest ratio. And the 2 other really important words that we have are coefficient and subscripts, right? Subscripts tell us how many atoms of each element are in the entire molecule, and then the coefficients tell us how many whole and complete molecules we have. Get those words locked in because they are words that we're going to be using like all of the time. So moving right along, how do we make a chemical formula? How do we write it? Here's the thing. First off, positive goes first. How often does positive go first? Always. Look at this. Learn this. Know this. Please have this memorized. Positive is always first. It will make your life so much easier if you can just memorize that positive goes first. Always. Which one is first? The positive one. Hey, Stu, how often does the positive one go first? Every freaking time. Hey, which one is positive? The first one. How do I know which one's positive, which one's negative? The first one is positive. Am I making myself clear? Okay. All right. I hope so. So let's move on here. Wait for someone to pick a nice color. What's a good color? Let's do brown. Okay. So first thing we need to know is that it is always positive and then negative. Positive is always first no matter what. And then the other thing we got to get down is that all compounds are neutral, so everything has to add up to 0. Again, it's because if stuff had charges, the whole universe would be like static electricity, and everything in existence in the entire universe would glom together in one giant ball, and we wouldn't have a universe. So that's why, right? So we have to balance them. We have to have a proper ratio so that all the charges add up to 0. So what we're going to look at here is primarily ions bonding with ions. We're not going to dig too much into how nonmetals bond to nonmetals because the covalent bonding can be pretty crazy. I mean, you make everything in biology comes from almost everything from biology is made of covalent bonds. It's pretty intensely amazing and diverse and just amazing the difference and crazy things that can happen with nonmetals. So we're going to start out with just ionic things. Okay, so let's dig in here. So here we have sodium. Sodium is a +1, and here's chlorine. So the ratio is just going to be a 1-to-1, right? Because sodium is a +1, chlorine is a -1. That's our chemical formula. We know that's our chemical formula because everything adds up to 0. Super easy peasy, right? Now, same thing. Here we have magnesium. It's a 2+. And since fluorine here is only a -1, we have to have 2 of them, right? So we're going to have a 2-to-1 ratio. You know, and so this is our formula. And I'm wondering if you might see a bit of a pattern here, that the magnesium is a 2+, the fluorine is a 1. We have 1 magnesium and 2 fluorines, right? I wonder if you're seeing that, right? Like the charge is 2, so of magnesium is 2, so I have to multiply the charge of fluorine by 2, and if the charge of fluorine is 1, I have to multiply the charge of magnesium by 1 to get a balanced chemical formula. Let's see if it keeps going, right? So the charge of aluminum is 3, the charge of oxygen is -2. So I'm going to have to multiply the charge of oxygen by 3 and the charge of aluminum by 2, right? So I'll need 2 aluminums and 3 oxygens to get my balanced chemical formula. And this is what we call the crossover method. It's a shortcut to writing a chemical formula if it's not really super straightforward. Like sodium chloride is pretty straightforward. +1, -1. You only need 1 each. But when charges start to get a little messy, the easy thing to do is the charge of your positive becomes the subscript of your negative, right? Charge of the positive becomes the subscript of the negative. And then the charge of the negative becomes the subscript of the positive. Do you guys kind of see how that works? We call it the crossover because you take the charges, you cross them over, and make them into the subscripts. It's a shortcut. It works perfectly. Let's give it a shot. So here's this. The crossover method for magnesium and chlorine. So magnesium is a 2+. Chlorine is a -1. And so we just take the 2 for the magnesium, becomes a subscript for chlorine. The 1 for chlorine becomes the subscript for magnesium. MgCl2. Easy peasy. Now this one we have to be careful about, right? So in this case, we're going to take the 2 from the magnesium, we'll drop it down to the oxygen. We'll take the 2 from oxygen, we'll drop it down to the magnesium. But this is a bit of a problem. We have to reduce, okay? Because if magnesium is a +2 and oxygen is a -2, really the ratio that we need is a 1-to-1, right? We only need 1 magnesium to cancel out the oxygen, right? And we only need 1 oxygen to cancel out the magnesium. So this is the one failing of the crossover method, is that you must simplify. You have to first cross over and then simplify, and then you're golden every single time, as long as you check the simplification, because this is the proper ratio. The ratio is 1 magnesium to 1 oxygen. Yeah, that's a little better. 1 magnesium to 1 oxygen, right? So you cross over, simplify. And this is the example for why we have to simplify, because sometimes when you do the crossover, the ratio is not quite right, but you just have to simplify it and then everything works out beautiful. So it's crossover and then simplify. Let's give it a shot with these guys. So I'm just going to write my elements down here. I have carbon with a +4, oxygen with a -2. I'm going to take my 4, I'm going to drop it down here. C is O4, oxygen is a 2. I'm going to drop it right there. However, I need to now double check. Can I simplify this? And yes, so this is going to turn into CO2, carbon dioxide. Beautiful. Easy. Next one. I'm going to take the 1 for the going to take the 1 for the hydrogen. There's my 1. I'm going to take the 2 for the oxygen. H2. Can't simplify. Good. Lovely. Let's take on this one. NH4, polyatomic ion. Now guys, when there's a polyatomic ion, you have to write down the polyatomic ion just as it appears. You cannot mess around with the subscripts because that changes the polyatomic ion, right? Can't change the subscripts. Can't change that to N2H5 or N2H8, nothing like that. And here's S. Okay, so I'm going to take, just like before, I'm going to take my 2 for my sulfur. I'm going to drop it down here. I'm going to put 2 here. I'm going to take, well, there's only 1. That's a 1, so I'm going to put it right there. Okay, so I'm done, right? No, of course you're right. I am not done, because that is silly. There's not 40. We are not trying to say there's 1 nitrogen and 42 hydrogens. That's just crazy pants. What I'm trying to say is that there are 2 NH4s, right? So to indicate, so for that subscript to say that there are 2 NH4s, you've got to block it off. You have to block this off like this. Sort of package it up with these parentheses. That way this 2 applies to what it's right next to. There are 2 NH4s. You got that? So when we're dealing with polyatomic ions, you need to treat the polyatomic ion as if it is 1 block. It's 1 chunk of a thing, right? So if you ever add a subscript to a polyatomic ion, you got to package it up so that subscript applies to the entire polyatomic ion. Dig it? Dug it. Awesome. Okay, moving on. The last thing I want to talk to you guys about with chemical formulas are hydrates. So hydrates are these weird little things. They are ionic compounds that have water bonded in the crystal. And how it got there is that when we make ionic substances, we basically crystallize them, right? So the chemical reaction happens, we get these ionic substances, they're almost always dissolved in water, and then we basically like dry out the water. It's a lot like making rock candy. But because of hydrogen bonding, and also because of like the way that the ions sort of like stack one on top of each other with water stuck to them, see, because there's an oxygen, hydrogen's going to stick to it. Inside the crystal of inside the ionic crystal, little water molecules are like all wedged up inside the crystal, stuck by hydrogen bonds. So that's kind of how it gets there, right? However, we can like cook them out. So you just put these hydrates in an oven and you can basically like just steam off the water. Okay? So that's what a hydrate is. It's basically an ionic substance with water bonded inside the crystal. And the number of water molecules comes after the formula, okay? And I want you to like I cannot see this little dot here. That means hydrate. They go dot, so many waters. That dot means hydrate, and it tells you how many. So this is saying copper 2 sulfate pentahydrate. So that dot right here says that it's a hydrate, and there are 5 water molecules for every 1 copper 2 sulfate. Got it? Good. So again, the number of waters comes after the chemical formula, and this dot, that big black dot, is what indicates that it is a hydrate, and this is how many waters are stuck to this particular hydrate. Okay? Awesome. So what that means is if we do a count here, there's 1 copper, there's 1 sulfur. For oxygen, there's 4 here. There's 5 times 2, there's 10 hydrogens, and 5 times 1, there's 5. So in all, there are 9 oxygens in all. Does that make sense? And something else that's going to be a little bit trippy when we start looking at this, if we add a coefficient to the front, like let's make 3, that means there are 3 of these, like 3 of the entire hydrate, okay? Not just copper sulfate, it is 3 copper sulfate pentahydrate. Okay? Keep that in mind. Moving on. Finally, to naming. Now here's the deal. When we name these things, there are only 3 categories of namings. There are only 3 rules. And the rules do not overlap. There is 1 category of rules for 1 category, and if you're in that category, that's what you do. There's a second category, and if you're in that category, that is what you do. And then there's a third category, and if you're in that category, that is what you do. These do not overlap, okay? So the first thing that I want us to remember is that all compounds end in "ide." That's how we know it's a compound. So when I say sodium chloride, the sounds coming out of my face indicate that you have a compound. It is the compound sodium chloride, which is much, much different than saying sodium chlorine. Sodium chlorine means I have some elemental sodium and some elemental chlorine. That you do not want to put that in your food. You stay away from sodium. And if it is chlorine, you stay away. They are deadly bad. Sodium chloride, delicious on your French fries. Right? So we end everything with "ide." And here's the deal. We got 3 categories. The first category is polyatomic ions. We're going to talk about that. The second category are metals, and our third category are nonmetals. And this is only if every single thing, everything in the compound is a nonmetal. It's the only way we can touch that third one. Okay? So let's dig in here for a minute. Oh, let me grab this, move it over. So for polyatomic ions, here are the rules. Not that. First, you look up the name. Actually, first you have to recognize that it is indeed a polyatomic ion. Once you know that it's a polyatomic ion, you go, what is it? Table E has all the polyatomic ions you're ever going to need. You look up the name and you write it down and you're done. That's all you do for polyatomic ions. We're done. Okay? That's it. That's all. It's super easy. It's on table E. Now, second category. Moving on to number 2. If there is a metal in the compound, so that's what you do. You start at the left. You go, oh, metal. If there's a metal, we're gonna follow metal rules for the metals. So let's see here. The first thing we got is this one, not that one. If there's only one charge. So for example, if you look at the metal and you see like sodium, you go to periodic table, it has +1. That's it. If you go to calcium, it has +2. Only one charge option. You just write down the name of the metal. And that's all there is to it. You just write down the name. Okay? That's it. So if it's sodium, it has one charge option, you write down sodium. Now, the same thing, only it's going to be a little bit different here, is if you go and you look at the metal, and there are multiple charge options. So for multiple charge options, that's like if we look at copper. Copper has a +1 and a +2 on the periodic table. Iron has a +2 and a +3. Some of them have like majillions of them. So if that's the case, if there is more than one kind of ion, we need to use Roman numerals that tell us the charge of the metal. So the Roman numerals go only to the metal, and the Roman numerals tell us the charge on the ion. It tells us which ion it is, right? Because copper 2 is like a vital nutrient. We absolutely need to have iron 2 or our blood doesn't work. Iron 3 is garbage. It doesn't do anything for us. Nothing. The difference between copper 1 and copper 2, one of them is green, kind of lime green. It's like what you get with the Statue of Liberty. And the other one is like an unbelievably brilliant blue. It's beautiful. So that's just the color. So, you know, again, in class, so many times things that we learn like, oh, copper 1 or 2 or iron Roman numeral 2, iron Roman numeral 3, it means nothing in a classroom until you go out into the world and actually try to apply it. The difference between iron 2+ and iron 3+ is night and day. They don't look the same, they don't act the same, they don't taste the same, they don't behave the same, they don't react the same. They are totally wildly different. They came from iron, right? They started as iron, but now they're ions and they are completely and utterly different, right? It's like siblings. They came from the same parents, but man, are they different. I haven't met 2 siblings that are the same yet. Not yet, anyway. All right, moving on. This next category is only if everything in the entire compound is a nonmetal. What we're going to do is we're going to use prefixes. And the prefix is going to tell us how many atoms there are. However, this is a little bit weird. If there's one of the first element, we skip it. Like this one. We don't say monocarbon dioxide. We say carbon dioxide. If we see this, we say dinitrogen tetra oxide. The prefix tells us how many. And the reason being that nonmetals combine in the weirdest, most random, crazy, mixed up ways. So it's not just crossover. Like, no, nonmetals do wild bonding. So we just use prefixes to tell us how many atoms there are in each one. Got it? So let's review. Polyatomic ion. If you have a polyatomic ion, you look it up, you write down the name. That's it, you're done. If you have a metal, there are two directions you can go. You have only one charge, and if there's only one charge, you write down the name. That's it. If there's multiple charges on the metal, you have to use Roman numerals to tell us what the charge is on that particular metal ion. That way we know which ion we're dealing with, right? And then the third category and the last one is if everything in the entire compound is a non-metal, we're going to use a prefix to tell us the number. And I will give you the prefixes. You don't have to memorize the prefixes. I don't care about that. I'm not testing you on memorizing prefixes. And the only weird thing about the prefix is that if there is one of the first element, we drop the prefix thing. I'm not exactly sure why, but we do it all the time. Carbon dioxide, carbon monoxide. It's not monocarbon monoxide. It's not monocarbon dioxide. It's carbon dioxide. Got it? Good. That is awesome. Oh, hey, there's the bell. Alrighty, so, all right. Here we've got a bunch of compounds. Boy, we got a whole bunch of compounds here, don't we? So, oh, and some names. Okay, so we have some stuff to do here. So let's go from, I guess here we're gonna go from compound to name, and then down here we're gonna go from name to compound. I like that. Let's dig into these, man. Shouldn't be too bad. Shouldn't be too bad because we know the 3 rules, and we're just gonna review the 3 rules. So when I look at this guy, I'm gonna see K. K is potassium. It's a metal. So the first thing I'm gonna do, I look at my reference table, and potassium is a metal with only one charge, so I'm just going to say potassium. That's a U. And then since it's chlorine, I'm going to end it with ide. So we end chlorine with ide in like a 2-beat kind of thing. So it's not chlorine-ide, it's chloride. So this is potassium. Potassium chloride. Nice. Next, Mg, that's magnesium. Okay, it's a metal. So anytime there's a metal, I got to go to my reference table. I got to check the charges, see if there's only one charge option or if there's more than one. Let me see, magnesium. Magnesium is in group 2. It only has one charge option, so I just say magnesium. And then here I have sulfur. So I need to end sulfur with ide in a 2-beat, like a 2 count. So it's not going to be sulfuride, it's going to be sulfide. So this is magnesium sulfide. Okay, are we getting this? All right, aluminum. Aluminum is a metal. So I'm going to go to my reference chart here. Aluminum has one charge option. It only, in other words, it only makes one ion. So all I need to do is write aluminum. And then nitrogen, I end in ide, in like a 2-beat. So nitride. It's not going to be nitrogenide, it's nitride. So this is aluminum, aluminum nitride. Nice. So next, I'm going to move my face over here so I can do that guy over there. So here we got calcium. It's a metal. So I'm going to go back to the reference chart. See? Yep. Calcium has one charge option, so all I need to do here is write calcium. Oh goodness, and look, 1, 2, there are 3 capital letters. There's an O. That's going to be a polyatomic ion. Do you guys see how this right here, it's more than one element. It's got to be a polyatomic ion because we are doing one positive thing and one negative thing, and that's it. Like, we're not doing like 4 or 5 different kinds of ions. There are just going to be 2 different kinds of ions bonding. That's it. 2 ions. That's it. That's it. So if there's more than 2 elements, then you have to have a polyatomic ion in there. I mean, does that make sense? So because it's an OH, it's got to be a polyatomic ion. Table N. Give me a second here. All right, table OH. Yeah, right here. Okay, OH, it says it's hydroxide. So what we do with polyatomic ions, you look up the name, you write down. That's it. Look up the name, write down the name. Wait, where'd my pen go? Calcium. Right? So I just looked up what OH was, and then I write it down. That's all. That's all you have to do for that. Got it? Let's keep going with these. HSO4. So hydrogen's a bit weird. If you look at the periodic table for hydrogen, you're going to have a +1 and you're going to have a -1. But the thing is, hydrogen's so weird. It's just so weird. So we just, okay, dude, I honestly, I just can't even. So we just say hydrogen. That's what we do with hydrogen. Now the other one, SO4, I see a polyatomic ion. What are the rules for polyatomic ion? Dude, you just look it up. So SO4 is sulfates. This is hydrogen sulfate. Did I spell that right? Yeah, hydrogen sulfate. Delightful. It's almost like I'm getting the hang of this thing, right? Like there's like these metals, and you just look at the metal. If there's more than one charge, or if there's just one charge, you just write it down. If there's more than one, then we'll have to do the Roman numeral thingy. let's just keep going with what we got here. All right, sodium. If I look at the periodic table of the elements, sodium, one charge. So I'm just going to say sodium. There's that OH again, right? That OH, that's my hydroxide. Right? It's the exact same as this guy right here, right? Same exact polyatomic ion, the OH. So I'm just going to write down OH because I can. So I'm going to. So let's do this one now. All right, here we have Na. We just did sodium. It's only got one charge, so I'm just going to write down sodium. And then CO3. See that? Definitely two elements. So yeah, that's going to be a polyatomic ion. Let me look up what CO3 is called. You know, I should really have these memorized by now, but I just don't. CO3. Ooh, carbonate. Okay, so this is going to be sodium carbonate. Delightful. Delightful. Are you guys kind of getting the idea here? All right, so now let's do titanium. All right, TI's titanium. Oh boy. All right, on my periodic table, I'm seeing titanium with +2, +3, and +4. So what this means is I need to figure out what charge is attached to this titanium. So first I'm going to write titanium. Okay, now over here is where I'm going to do my little bit of work. I've got titanium, I've got my chlorine, right? And just like what we learned today. First you do the numbers. That's going to be 1 titanium. There are 4 chlorines. And then my second line, that's where I do the charge. Excuse me. So for the titanium, I don't know. It just says titanium. It's going to be titanium 2, titanium 3, titanium 4. I have no idea. So I'm going to put X because that is what I'm looking for. All right. Now chlorine is on the right. So that means chlorine has to be negative. And if I look at the periodic table, the only negative option for chlorine is -1. So what this is saying is I have 1 titanium atom. The charge on that atom is X. How much charge in all? X. I have 4 chlorines. Each chlorine is charged -1. How much charge do I have in all? -4. Now these things all add up to 0, right? Because that's the charge of the compound. So this gives me X equals 4. So this will be titanium 4, because I use my Roman numeral to tell me the charge if there's more than one charge. Huh? Nice. So this is that's how I find out the charge of my metal. Right? All these other ones up here, it was really simple. Sodium is just a +1, so I just write sodium +1, magnesium, aluminum, calcium, potassium. They are all They all have one charge option. They can only do one thing, so we just write down the name and that's it. But now we're getting to this guy over there, titanium. Now titanium has multiple charge options. So how do I know which titanium it is? I don't, unless I figure it out. And that's what that whole mess over there is all about, right? This is all about finding out what is the charge of my titanium. Turns out the charge on this particular titanium, that's supposed to be an arrow, is 4, so I call this titanium 4 chloride. And I'm going to erase my work so I can get it out. You might start seeing that you might need some scrap paper to get through this. Maybe. All right, this next one, Cu is copper. And let me check the periodic table. Copper has multiple options. Copper can be +1 or it can be +2. So I don't know what the charge of copper is. So I'm going to come over here. I'm going to figure it out. So I've got CuSO4. Remember, the number goes first. I've got 1 copper. And what we saw today is that when you have a polyatomic ion, right? This is a polyatomic ion. Let's treat it like one thing. It'll save us a lot of extra stupid work. So we're going to do 1 polyatomic ion. What is the charge of my copper? I do not know. I'm going to find out. What is the charge of SO4? I got to look that up. Go. Turns out SO4 is going to be -2. So 1 copper with the charge of X. I have a total of X from copper. 1 SO4 with a charge of -2. How much in all? -2 in all. These all add up to 0 because it is a neutral compound. Therefore, X equals 2. So this will be copper, Roman numeral 2. Oh, and then SO4, sulfate. That was super duper awesome. Do you guys follow how that went? I certainly hope you did, because I'm going to move on to this one. All right, copper. Once again, I've got copper. I got to do my thing over here again. All right, so I've got Cu2SO4. How many coppers? This time I have 2 coppers and still 1 SO4. Copper is the unknown, and the SO4 is -2. I just looked that up last time, right? So if I have 2 coppers, each copper has a charge of X. I have a total of 2X charge from my copper. Excuse me, I have 1 SO4. Each SO4 is -2. I have -2 in all. These all add up to 0. So 2X minus 2, X equals 1. So this over here will be copper Roman numeral 1 sulfate. Again, when we're just sitting around in a classroom, it doesn't look like much, but man, in reality, these two things are totally, wickedly, crazily, absolutely different entities, man. Like these should not be confused as the same thing. So let's keep going. Fe is, wait, where'd my pen go? There it is. It's iron, so it's going to be iron. Let me go check if what I got. Oh, more than 1 charge for iron, definitely. So let's do this. Actually, let's do this here. I've got 2 irons. I've got 3 oxygens. Iron is my unknown, so the charge will be X. And oxygen has a charge of -2. So I have 2 irons. Each has a charge of X. How much charge in all? 2X. I have 3 oxygens. Each oxygen has a charge of -2. How much charge in all? 3 times 2 is -6. Now this is all going to add up to 0. X equals 3. Yeah? So this is going to be iron, Roman numeral 3, oxide. You with me on that one? Awesome. So these first two rows, metals with only one charge, and then mixed in some polyatomic ions. This whole row, every single one of these guys, all these metals had multiple charge. So I had to go through and do that thing to find out what which charge I actually had there, and then that charge, write it down as a Roman numeral, and then you just name the polyatomic ion or whatever it's attached to. Now this down here, these guys, these are all going to be non-metals, right? Non-metal, 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 they are all not. This entire compound is non-metal. That means I can follow just the prefix rules, okay? So for my just prefix rules, I'm going to, okay, there's only one carbon, so I'm just going to say carbon. And there's one oxygen, so it's mono for one, or monoxide, carbon monoxide. You dig what I'm saying there? That's carbon monoxide. Now this next one, carbon, there's only one of the first one, so I just say carbon. Right? And now it's all non-metals, so I'm in the prefix zone. All I do is use prefixes, that's it. There's two oxygens, so the prefix for 2 is dioxide. Remember, everything ends in "ide." 2 count beat, oxide. But there's 2 of them, so we say dioxide. Carbon dioxide. Right? Let's go to next. So now we have, there are 2 nitrogens. That's not 1 anymore. So again, using prefixes, mono, di, tri, tetra, penta, hex, hept, oct, non, dec, or des. I don't care. I'll write out the prefixes if I have to. It's, again, I don't expect you to memorize these, but I just want you to know that you should use them. So the prefix for 2 is di. So this will be di, nitrogen. And then the prefix for 4 is tetra. And then oxide. That's it. There is a worksheet where we're going to work on this, and the prefixes are listed. So you will not have to look up you won't have to memorize the prefixes. I really want you guys to like simmer on that and be okay that this is not going to be like a thing that you have to memorize. Now this next one, phosphorus, there's 2 of them, so it'll be diphosphorus. Wait, how do you spell phosphorus? Diphosphorus. The prefix for 5 is pent, like pentagon. Pentoxide. Yeah, good. Does it make sense? This is what I mean. These guys right here, these 4, these are what I mean. So when we name something that is, what I'm trying to say is, I'm going to cut this during the recording. So all of these examples here, every element is non-metal. Not just one of them, not just 2 of them, but like every single bit of these compounds are non-metals. That's when we're going to use the prefixes. And that is the only time we use prefixes. When all of them are going to be non-metals, not just like a non-metal here with a metal. It's everything in it needs to be non-metal. That's when we can use the prefixes. Okay? Awesome. Now, moving on to our next and final bit of stuff of learning is going from names to formulas. Now, this is going to be a little bit easier, especially with the Roman numerals. Because if it's iron 2, you just go Fe for iron, and it's going to have a 2+. And we're going to erase that at the end, because formulas don't have charges, but it helps us balance. And then chloride. And since it's on the right, it's going to be negative. And then you look at the table, it can only be a -1. And now you use the crossover method. So if the charge is 1, you get 1 chlorine. If the charge is 1 iron, if the charge is 2, you get 2 chlorines. And then I got to get rid of my charges. That's my chemical formula. That's all there is to it. Same thing, only a little bit different. We're going to have iron, but this time it's going to be a 3+ chloride. Still a -1, always going to be a -1. Then we take our charges, drop and swap, cross them over. Because first you got to drop and then you flippity flop. So if you got a 3 for your iron, you make it a 3 subscript for your chlorine. If you have a -1 charge on your chlorine, you drop that over, a 1 on your iron. There you go. That's iron 3 chloride. Now this one, copper 2 hydroxide, we're going to have copper with a 2+, and hydroxide. That is a polyatomic ion. That is OH with a -1 charge. Table E. It's all there on table E. So to draw the balanced chemical formula, I take the 2 for the copper and I put it out here. But because it's a polyatomic ion, don't forget, you got to like package this together as one unit, and then you can put your subscript of 2. Because you need to say that there are 2 hydroxide ions, not 1 hydrogen, or not 1 oxygen, 2 hydrogens. You must be very clear that there are 2 OHs. Yeah? And then your 1 from your hydroxide, you'll drop that down to your copper. Come out and erase your charges, because charges don't go on formula, and you're done. And actually, you're done. Finally. And now we're done. All right. Thank you for hanging in there. This was a huge one. However, I think you guys are going to get it. You guys are doing pretty good. Have a wonderful day.